Okie dokie. So today we're going to start talking about model selection. And this is a theme that will be coming up in the next couple lectures as well. Okay, so let's talk about what this is. So model selection. The task of selecting a statistical model from a set of candidate models. So suppose we have something like, suppose we have the data y, x1, x2, x3, all the way to xn. The question is, which model is best? So this might be something like y equals beta 1 x1 versus y equals beta 2 x2, and so on and so forth till you have basically all combinations. Something like this. Okay. So last time we had talked about, at the end of class, cross-validation and using mean squared error as your metric. But there's actually a couple other methods that we'll discuss here, which can, in different ways, give you some perspective about how well your specific selected model would do. And these metrics are, I think, mainly useful for comparisons against other sorts of model selections. So you wouldn't necessarily use these as criteria between completely different models where you are looking at different response variables. But if you are choosing like a consistent set of data and you are constructing models that help describe your explanatory variable, this would be a good time to use it. Oh, I'll just mute him. Okay, so moving on. So here are, we'll sort of go through some common criteria for model selection. So the first you may have heard before is known as the Akaky information criterion. So this is called AIC. So this is an estimator of the relative quality of the statistical model. And the smaller it is, the better. Okay. I will write out the equation, but this is, again, one of these things that we won't delve so much into the theory here, but more sort of for your reference. So 2k minus 2 ln L hat. Okay, so what is this? K refers to the number of parameters. And this big L hat is your maximum likelihood value. Okay, to give you sort of a qualitative sense of what this means, right? As we discussed before, generally your model will always do better with more variables. Okay, so if I were to add, for example, if I go back here, if I were to think about this model versus this model, as you include more ways to capture, or as you include more degrees of freedom, it's always going to get a closer fit to your data. And so the way that the AIC prevents overfitting is that it has this term here, which essentially penalizes, it's a penalty function for the number of parameters that you're getting, right? So the more parameters you have, the larger your AIC becomes. But the trade-off is that here you are getting closer and closer fit in your model, and so it's saying, okay, I'm going to reward you for getting close to for having a better fit, but I'm going to penalize you for having more parameters. And so it finds some kind of balance between these, so that it doesn't overfit the data, but it can get sort of the best possible fit without having too many parameters. So in concept, it's kind of similar to what we talked about before with the cross-validation and auto-sample validation, right? These are ways that we are attempting to balance between specific variables and choices of variables in your model, and preventing overfitting.
Alan, can I ask a question?
Yes.
Is there a significance for the coefficient too? It just looked like we could do without it.
Yeah, so this gets a little bit more into the theoretical aspect of like how they came up with this. So when I say, oh, there's this trade-off between number of parameters and the maximum likelihood value, you have to make a decision about how you sort of weight it. And so that plays into the formation of this. Specifically with the two, I guess you're asking about just dividing by 2 on both sides, right? There are forms of, there's actually convenient forms of transformations of the AIC that take advantage of this, where, so for example, oops, what did I do? So in a linear model, people often use this to calculate the AIC. So this is AIC for linear models. And I believe, I'm not 100% sure, but I think that the 2 in one case just makes the substitution easier to turn it into this. But I'm not entirely sure about that.
No, thank you. I was just curious.
Yeah. I think it's a product of how it's sort of originally derived, and I guess qualitatively, if you just divide it by 2, it's not going to change anything, because it's all going to be, you're trying to measure AIC in one model against AIC in another model. So yeah, it shouldn't really make a difference. Okay. So that is our sort of first one. Another criteria is known as Mallow's CP. Okay. So this one is actually pretty similar to AIC. So this reduces the RSS, which is the residual sum of squares, while taking into account the number of parameters. And the differentiation for AIC and Mallow's CP comes more into play in different types of models. And in fact, is this actually going to be equivalent to AIC for linear models? And I mean that sort of proportionally. So CP is equal to 1 over n of RSS plus 2 K, like that. So this is sample size. Again, in this case, you want your CP to be as small as possible. So this is your residual sum of squares. This is your number of predictors. And this is your estimate of variance. Again, you don't need to worry about like memorizing the equation or anything. But this is, again, similar in concept, right? So when we talk about the overfitting issue, this is your penalty function for having more predictors, right? So as you add more variables into your model, your K gets bigger, which causes your CP to get bigger. And then the larger your errors are, right? So the farther away the actual points are from the fit of your line for your residuals, and you add that all up, this will get bigger. So as you increase K, your RSS will always get smaller, right? So it'll typically look something like this. don't really have a lot of room to draw this. Or we'll just do it in a different color. So we'll do a more sort of formalized version of this concept of overfitting, but generally when you have very few parameters, as you have very few k, the residual sum of squares, in other words, the sort of general metric for the fit of your model is going to be bad. And then as you get more and more, it's going to improve. Oops, sorry, this is not right. Hang on. It'll look something like this. But if I were to graph it against the MalloCP or AIC for that matter, you're going to get let's see, you are going to get something qualitatively that looks like this. So CP or AIC, as you add more and more parameters, it'll penalize it. And actually you may start sort of you may actually start a little bit higher here. Okay, and we'll see this concept a little bit more formalized in a future lecture. Okay. Moving on. The basic structure of the equation, right? So in the Akaky information criterion, it's 2k minus 2 natural log times your maximum likelihood value. There isn't, that's one set of weights for deciding how much I value having more parameters versus having a better fit. And so it's not the only one, right? So the MalloCP is a different way of doing it. And there's one that has been developed based off of the AIC, known as the Bayesian information criterion, which is, again, same concept, but the way it chooses to value the parameters versus the fit is slightly different. And I guess the reason why I'm introducing this is because these are all criterion that are fairly commonly seen in a lot of these data analyses and statistical analyses. But at the end of the day, it's kind of up to you and your own assumptions about what criterion you use. And in my opinion, it's not, it'll definitely give you different answers in terms of like when you do the model selection. It would not be uncommon to find, if you were using BIC versus AIC, that it would say, oh, include like X3 and X4, but not X5, versus just include X3. That would be that's an artifact of the assumptions of the criterion. But at the end of the day, like, you get to choose what that is. And so I would say, it doesn't make a huge difference for determining your model based off of whatever you select. Just want to give you the full toolbox here. Okay, so BIC is equal to ln n times k minus 2 ln. So really quite similar. Again, better if smaller, bigger penalty on models with more variables. So notice the main difference is that the 2 in the AIC is replaced with ln of n, which is this is number. It's called it's the sample size. And in the linear model, this is something also quite similar. Log of n times that. And so this is a linear model. Okay. So that's AIC, MALA-CP, and BIC. These are used in lots of different models and applications. Oftentimes the choice of them more comes down to what people commonly use. But they're going to give fairly similar, but not always the same answer. And then we'll talk about one last one, which is the adjusted R squared. So we've talked about the R squared before, and that's just 1 minus the residual sum of squares divided by total sum of squares. And we modify the R squared, and I had talked about this before, but now we'll sort of formalize this with this term, n minus 1 over n minus k minus 1. So this, again, is the same concept of trying to deal with overfitting, and it introduces a penalty function for having more variables, right? So as k increases, then your denominator gets smaller, right? It's because you are subtracting. And if you divide by a smaller number, then your term here will get bigger, right? So, okay, maybe I can write out the logic like this. As k increases, then n minus k minus 1 decreases, then n minus 1 over n minus k minus 1 increases. And so let's see, when this term gets or let's see, when this term here gets multiplied against a larger term, then this whole thing will increase, and so your adjusted R squared will decrease. So all else constant, right? But it's balancing against the fact that as K increases, then your RSS will decrease. So this could lead to adjusted R squared going up. So you are balancing between what's happening here versus what's happening here. And so you end up getting a balance between your adjusted R squared increasing and decreasing, and you basically have the same sort of concave function that I was drawing before, where at some point the addition of more parameters is causing your adjusted R squared to fall faster than the gain that you get from the fit. Okay, so at a high level, let's talk about some of the differences between any of the criterion. So first of all, when we think about the adjusted R squared versus AIC, CP, and BIC, R squared tells you more about how well, how well does your model explain observed data? Whereas your AIC, CP, BIC explains how well will your model fit new data. Lower means better prediction. One of the nice things about R squared is that you're always going to be essentially between 0 and 1. So it's standardized across all sorts of models. But with AIC, CP, and BIC, they are particular to your set of data, right? And so you can't really compare, AIC for one type of model from one data set versus an AIC from another model using a different data set. And as I talked about throughout these criterion, all of these things are penalizing more parameters, right? I would say in general, R squared is more popular, but less statistically strenuous. Okay. Sort of diving a little bit more into the differences between the first three criterion, so AIC, CP versus BIC. So we won't really get into the theoretical reasons for this, but BIC is argued to identify the true model as n approaches infinity. So as you get more and more data, as you get more and more data, the BIC is better able to tune the model because it includes the sample size as a parameter. Whereas AIC minimizes selecting a bad model with small sample size. So people will often say you can use like BIC with large sample size models, and you would use AIC for models that have small sample size. But the sort of cutoff and threshold between small sample size and big sample size is fairly ambiguous. And so, oftentimes it's just worth doing both, and it's not so hard to do that. And then, sort of as a backdrop to all of this, you can also directly estimate test error with cross-validation. So that's exactly what we talked about last time. And so the procedure of doing like cross-validation, that is a criterion for model selection as well. And I think is probably more robust than any of these, which are generalized formulations to try and get the balance between fit and number of parameters, whereas the cross-validation explicitly tells you what the best fit versus having too many parameters, because everything that you're doing is from a test set out of sample. I think the traditional reason why people use AIC, BIC, adjusted R squared instead of doing that is that it used to be a lot more computationally intensive. And so these are quick and dirty ways of being able to approximate what your cross-validation is doing. But given how well your cross-validation sort of is really doing it, I mean, it's the real way of testing, right? Because you're really doing actual prediction. I would generally sort of prefer that unless you're just trying to do like quick and dirty checks. Okay. Do we have any questions about this? I feel like I blazed through this pretty quickly. No questions. Everyone's got this on lock.
I have a question.
Yes.
How do you calculate L hat?
Okay, yes. So the maximum likelihood value. I'm trying to think if we should, well, the maximum likelihood estimator is it's a different way of getting it's a different way of getting your model that we use in certain regression applications. So, so for those of you who aren't familiar, we've talked about in a linear model, you want to minimize this. You want to minimize the sum of the squared residuals that gives such that it gives you the best line, and that is a type of optimization. There are alternative ways to estimate a fit, which tend to be a preferred method in certain applications, and that is known as maximum or maximizing the likelihood. And so you have a likelihood function for your model, and let's see. I'm not gonna. Yeah, I don't want to get too hung up in the theory of it. But I guess what I'll say is that the likelihood estimation is typically calculated numerically as opposed to in an analytical framework that we have in the linear model, where you're reducing the sum of the squared errors. And that is done sort of computationally. So my long-winded answer is kind of like the computer will do it for you. We will talk about some forms of likelihood functions when we get to logistic models, which use maximum likelihood. But yeah, so I'll basically leave it at that. I'll just say that that you don't need to worry about explicitly calculating the likelihood because the computer will do that for you.
Great, thank you.
Yeah. Okay. So with all these criterion, you may be thinking, okay, how do I sort of formalize and go about doing this? Because if let's see. Okay, let's see if we can work this out. So let's suppose I have y, x1, x2, all the way to xn variables. How many combinations of models are there? Who can tell me, or who can help me work this out? So, I can have all the single ones, beta 1, x1, all the way to beta n, xn. So that's n models. And then I have all the combinations of beta 1, x1 plus beta 2, x2, and then y equals beta 1, x1 plus beta 3, x3, and so on and so forth until I get to xn. Oops, beta n xn. And this is what, n minus 1. And you do that approximately n times. And so let's see, is that right? Will I have, and then you do the same for the triples, so you have n, I think you have n minus 2 models. So it's going to be, I need to check this. I don't have this like in my notes or anything. I think that the number it's definitely going to be exponential, right? You can kind of visualize that as I add more variables. If I were to try and if I were to try and calculate like the AIC and BIC for each of these models, that might be okay if you have, I don't know, 4 or 5. If I only have like 4 or 5 variables, but once you are talking about, in theory, maybe you're doing more of a machine learning approach where you're trying to brute force a model selection, and you've got, I don't know, 1,000 to 10,000 variables. This quickly becomes completely infeasible. And so how can we go about, actually applying the criterion that we talked about to an actual application of selecting specific variables for a model? Okay, and so next class we're going to actually talk about a more or sort of getting into some machine learning approaches to do that. But today we're going to talk about a sort of more simplistic approach that is common in a lot of basic statistics applications. It's kind of the one of the first developments for how to do or how to formalize model selection. And so this is called stepwise regression. It's also kind of controversial because there are forms of stepwise regression that are still taught in classes today that are just not correct. So I'll talk a little bit about that in a moment. So the larger the K, which is the number of variables we're selecting, the more combinations of variables there are. Oh, actually, I do have it written down. It's 2 to the K. Okay, hang on. Sorry, let me correct this. This is, it would look something like this. 2 to the N.
Hey, Alan.
Yes.
Would that include all of the interaction terms?
No, it would not. If you include all the interaction terms, it explodes even faster. And this is why I was saying, actually, even some of the methods that we talk about, it's hard to formalize for interactions. And maybe that's part of the limit of my knowledge in terms of how we approach doing the interactions, which is why I was saying like, oh, you should just base it off of what qualitatively, if there are like reasons to do the interactions. But I'll actually look into this a little bit more. And I can check to see if there are methods that integrate into things like stepwise ways to look at combinations of interactions. I'm personally, at this point, not aware of any that do that, which maybe is not to say that it doesn't exist, but I will look into that. So because you have exponentially growing combinations of variables with the more parameters that are available in your data, we need ways to walk through different combinations. And so stepwise regression is doing exactly this, and I'll describe sort of the algorithm for doing this. But it should be noted that that stepwise selection does make some sort of simplifying assumptions, right? And okay, I'll hold off on talking about that because I think it'll make more sense after I describe how the stepwise selection works. So we'll sort of write out qualitative step by step procedure to perform stepwise selection, and then we'll think about what it's actually doing. Okay, so forward stepwise selection. Okay, so 1, choose a model with no predictors. 2, for k equals 0 to total number of predictors k. Add 1 additional predictor. Test all different remaining predictors. And then, oops, what did I do? Select the best as having smallest RSS or R squared. Okay, I'm kind of running out of room, so I'm actually going to wrap around the top so that we can keep it all on one whiteboard for now. And then 3, select best overall based on selection criteria. So this might be your AIC, CP, BIC, and possibly even adjusted R squared. I personally would not suggest doing the adjusted R squared, but okay, so what's going on here? Basically, let's say we are looking, yeah, okay, so I think, okay, same question is coming up again. So what about interaction terms? In this case, the framework of how forward and backward stepwise selection, it doesn't do interaction terms. And so I will look into this to see if there are other methods of model selection that include interaction terms, but for now, I'll just say that, right, this doesn't do that. You could explicitly include all combinations of the interaction terms. So in this example that I was about to do, I can do y, I was going to say y, x1, x2, and x3. And that's kind of the set of variables that I'm doing my forward stepwise selection on. But you could just also include, x1, x2, x1, x3, and then x2, x3, and then you just have more variables to walk through. So it's possible to do that kind of manually in this case. Okay, so basically the way this works is it's going to look at this, beta 2 x2, y equals beta 3 x3, and then I'm going to I'm going to look for the one that has the best RSS. Okay, you should, I kind of wrote this weird, as having the smallest RSS or the biggest R squared, right? So you want the one with the best fit. And let's suppose that, the one that gets selected is this. So that one has, let's say, the highest R squared. Okay, so now we're going to proceed to the next step. So this is step 1. Step 2, we're going to take this and we're going to say y equals beta 2 x2 plus beta 1 x1. Y equals beta 2 x2 plus beta 3 x3. And now we're going to do the same thing and we're going to say, okay, which one has the best R squared? Okay, maybe it's this one. And then you proceed onwards, right? And so you can imagine that if I have k number of parameters, the number of models that I'm actually measuring are essentially going from 2 to the k to something like k squared. So it'll be much smaller in terms of the number of models that I need to run. Okay, and so now at the end of this, you end up with a whole set of models, so the ones that I have in red, and now you have to choose. So the one that I have in red is sort of like this, and then at the very end, you select the best one based off of your selection criteria. And so now I look at the AIC or BIC or CP for each of the models that I've select the best models at each step. And maybe I'll say, this is my best one overall. And then voila, there's sort of your final model selection. Okay. Anyone have any questions about this? Yeah, exactly. So in the chat, to clarify, each step involves adding a new X variable. Exactly. So you choose first the X variable in step 1 that does the best, then you move on and then you add one more X from the best model from before. Sometimes this is taught in a way where they are doing based on the significance of the variable, and so it'll say, okay, add them in by add the variables in until you don't get any more like significance. So you check all the variables first, and then you say, oh, which one has the highest level of significance, and then you choose that as your first step, and then in your next step you add another variable in, and then you see which one is the most significant or has the highest R squared, and you continue on in doing that until your R squared is not improving above a threshold, or the significance or none of the variables that you add lead to any more significance. Okay, don't do that. I don't know why they still teach this in some classes. It's been kind of debunked as a pretty terrible way of doing this. You can bias your model in all sorts of ways, and it's not going to be a good indicator of a quality of the model, especially because you could have non-linear relationships between the significance of your variables. So in other words, if you have multicollinearity in your model, for example, then choosing one variable based off of its level of significance and then adding other variables could actually alter its level of significance later in future steps. So yeah, if everything I'm saying isn't something that you've learned before, then don't worry about it. If you've been taught to do stepwise regression in that way, please forget about about that, because it's wrong. Okay. Looking in the questions, in step 1, do we use selection criteria or cross validation to select the best model? So I think what you're saying is here, can you use the other selection criterion, the AIC, BIC, or adjusted R squared, for example? So correct me if I'm mistaken. Yeah, so I think that you can. I don't see a reason why you can't. I've actually wanted this a little bit myself, but I never see it that way, and I'm not exactly sure why. I would imagine that that qualitatively, if you use the other criterion, you should be getting you should be getting no different than if you were to use the RSS or R squared. So maybe it's more of like just the way that people have been doing it in the past. I can look into see if there's a specific reason why we use RSS R squared in step 2 as opposed to the selection criteria. But generally, the way that I had written it out is the way that it's done. Okay. So that is forward stepwise regression. There's actually, as you probably can imagine, a different way to do this called backward stepwise regression. Oh, hang on. When I write on my iPad, my wrist touches the pen options on the bottom, and weird things keep happening. Stepwise selection. So this is same as forward, but start a model with all predictors and remove one at a time instead of adding one at a time. So instead of starting at k equals 0, you start at k equals a big K, and then you take one variable away. And you can get similar results, but not always the same. Okay, let's take a quick brain break, and we'll reconvene in 5 minutes at 11:10. So I'll answer questions at this time as well, but let me quickly get some water first. Okay. Let's continue onwards. And now for the second half of class, what I'm going to do is to show an implementation example for this forward stepwise regression algorithm, and we'll learn how to code that in R, but then I'll also show built-in functions that do that. So I've loaded a couple. I've loaded a couple packages here. So the stats and mass packages are packages that are going to let me do stepwise regression sort of automatically. They have built-in functions that do that, and we'll take a look at what those how to perform that after we sort of manually code it ourselves. The first package called ISLR is based off, it's not based off of, it's ISLR is actually a really famous introductory to statistical analysis, machine learning, kind of data analysis book. A lot of actually what we cover in this course, not everything, but a lot of what we cover in this course comes from that material. So it's a pretty handy, it's a really sort of friendly introductory course to this material. And they have a lot of practical data analysis examples and data sets of which we're going to be drawing from today. So I've loaded data called credit. Oh, I see a question. What's the name of the book? It's called, oh, actually, I can just pull it up real quick, and then you guys can see ISLR. It's called Introduction to Statistical Learning. Here. So these authors. Oh, hang on. Apparently you can get a PDF now. Is this? Yeah, well, there you go. You don't even need to buy it anymore. So I'll go ahead and put this in the notes right here. So when I post it, you'll be able to find it. Okay, so the package in R is basically a set of data and examples that they're using, which is pretty handy to show some of this stuff. So today we're going to be looking at a data set called credit. So it looks something like this. We have an ID, which is just an indication. Actually, since we're in RStudio, we can do this, which maybe is a little bit easier. Well, they're going to tell us slightly different things, but an ID for the person, and it's 400 observations. So you got 400 rows, so 400 different people. We've got income. This, I would imagine, is in the thousands, right? So 14,000 a year, 106,000 a year, so on and so forth. Average income is about 45,000. Limit is the credit limit that you have. Rating is probably some measure of, it would be some measure of like a credit score. It's not going to be the typical credit score that you see, like a FICO credit score, for example. Cards, it's probably the number of credit cards. You've got your age, number of years of education, gender, and then whether or not the person is a student, whether or not they're married, their ethnicity, and then the current balance on all of their credit. Okay. And so what we're interested in is the balance. So given people's, I believe this is average balance on a credit card. So given people's, income, their credit limit, their credit rating, the number of credit cards they have, and demographics, are we able to, or can we figure out what sort of the best combination of these variables are to describe and predict their average credit balance? And so the first thing that I'm going to do is, so let's think conceptually about what we want to do. I want to be able to essentially walk through all of these variables, income, limit, rating, cards, so on and so forth, in different combinations, right? So one at a time first, and then I take the best one in the first step, and then I take all the rest of them, look at them each individually, take the best one, and then progressively look at each combination of remaining variables. And so the first thing I want to do is to grab the names of all of the columns. So income, limit, rating, cards, age, education. Okay, the two that I'm going to leave out are the ones that I don't want in my regression, in my X's. So balance, which is what we're regressing on, the Y, and then ID is not a variable that we want in there. So I'm saying grab all the names, except don't include the ones that are ID and balance. So I run this, and I just look really quickly. This should isolate all of the column names for the ones we want to include in our stepwise algorithm. Okay, great. So isolating column names of interest. And then here, we're going to do our step forward regression algorithm. So I'm going to create my empty bucket. So this is the same trick that I think I've shown a couple times now for essentially storing outputs of a for loop. So all models, and then selected variables. So qualitatively, I can describe what's going to be going into these buckets in every step of my for loop. The all.models is going to hold the model that gives me the best R squared, or the best, or the one with the smallest RSS. And I'm going to take that model and I'm going to store it so that later on, when I do the overall criteria, I'll have a list of all the models that I stored. The selected variables are the things that, as I walk through the model step by step, I'm going to take out a variable, right? Because that's like, oh, in the first iteration of my for loop, maybe let's see, maybe the credit rating turns out to be the most important one. So I'm going to isolate that, and that's going to spit out into a selected variable, so that in the next for loop, it'll start with saying, okay, rating plus what other variable. So that's what these empty buckets are doing for now. So my for loop is going to be for n in 1 to the number of column names, right? So 1 to the length of the variables of interest, essentially. So we'll have available names. So this is going to be a subset of my overall credit names, because as I move through each stepwise or each step in this algorithm, I'm going to essentially say, right, if rating is the best one in the first step, I should no longer be selecting that variable in the following steps. So here, what we're going to do is we're going to say it's the subset of credit names where they're not in the variables that we've already selected. So here, just this part is saying available names is credit names, and then we don't want to include the credit names, so that's why there's this exclam here, that are in the variables that we've pulled out in our selected variables. And then I'm going to create a couple more empty buckets within the for loop, because in each step I also have to walk through all the available variables and then pick out the best model. So we're going to look at all of these, which are just placeholders for now. So these are buckets in the same way that I'm holding them outside for inside each loop of the available names. So here I'm going to have a second for loop inside, which is going to look at the available names. So let me draw this out so that hopefully it's a little bit more clear. If I have y, x1, x2, x3, and one more, let's say x4. So the outer for loop is the thing where you have, so outer loop is where you have the total number of variables. So it might be something like selection of x1 and then selection of x1 and x3, and then selection of x1, x3, x4, and then selection of x1, x3, x4, x2. So this one will have k, and that is this for loop here. And then the inner loop, oops, where's my eraser? The inner loop is the x1 versus x2 versus x3 versus x4. And then for the next part of the inner loop, if we choose x1, then it'll be x1, x2 versus x1, x3 versus x1, x4. These are just commas; they're not like multiplied or anything. Okay. So hopefully that's clear. If not, then you'll have to kind of review this on your own. But there will be actually a homework problem where we replicate this, except you're going to do, I believe on the homework, it's replicating this, but doing it with step backwards. So working through this yourself will be a good way of really familiarizing yourself with what's going on. So this is a way that I'm essentially formulating the model. This is going to create something that looks like, you know, rating plus limit plus income, depending on what step you are and what variables that you're adding in. So I'm not going to translate exactly what this means, but you can walk through this to see what's happening on your own. And then we're going to create our formula based off of that, where we paste balance, which is what we would have in our linear model, plus whatever variables are being held in any particular step. And then it's a matter of just running the model. So lm of formula hold, data equals credit. And then we want to hold on to the R squared. So this would be for an individual model run, it's going to hold on to that R squared. And so the logic of what I want to do now is I'm walking through each of these models. So beta 1, x1, beta 2, x2, beta 3, x3. And I want to basically hold on to the one that has the highest R squared. And so the way that I do that is I'm going to have this if statement. If R2 hold is greater than the one that I'm holding on right now for the best R squared, then I'm going to replace that value, and then I'm going to store that model. So best R squared is now assigned as the R squared, which I'm holding, which I see is bigger than the current R squared. And then it's going to take that as the current best variable that I'm going to hold on to for the next step, and it's going to hold on to the model. And that's basically it. We just need to, at the end of this, update our selected variables. And then give us all of the models. So in this case, it's holding on to each of the models at and each level of the best model, and then it's going to print all of these for us. Okay, so even if you don't follow along with everything here, let's just take a look at what the stepwise model is doing. And hopefully, again, as long as you have a grasp of the logic, that's more important than understanding exactly what the code is, because you can kind of figure that out for yourself, and you will be doing that on the homework. But let's run the code, and then we can describe what the code is doing. Okay. So in the very first step, it has essentially run, if I look at the data, it's run the regression balance on ethnicity, balance on married, balance on student, and so on and so forth until it's run every single one of those single models. And then it looks at the R-squared of each of those individual models, and then it says, okay, rating was the best one. So from here on out, in the next step, I'm always going to include rating. So now I've included rating, and I'm going to run balance on rating and one other variable. So it does balance on rating and ethnicity, balance on rating and married, balance on rating and students, and so on and so forth. And then it's going to look at the best R-squared out of all of those, which happens to be income. And so we're going to repeat this process all the way until we include every single variable. So we can see the order in which the variables are quote unquote sort of important. And so again, there are some simplifying assumptions, right? Like what if income is worse than rating on an individual level, but income and students could give you a better model than rating and income? In theory, that's possible. And it's something that a stepwise regression would miss. So it's a trade-off between this assumption about additivity in the quality of the model fit versus simplifying the complexity of going from 2 to the k down to essentially k or k squared number of combinations to look at, or total number of models to run. Okay, so that in the notes, what this model has done is implemented steps 1 and 2, and now I have this whole list of models where I know for basically the number of variables, the ones with the highest R-squared. Okay, so then how do I know that that this one is better than this one, right? So as you include more variables, again, you're always going to get a closer fit, but you run into the risk of doing the overfitting. So at what point can I make that trade-off? Well, if you guys remember to the rest of class that we've done today, we have a bunch of criteria with which now we can apply to these different models and determine which one gives us the best fit to overfitting trade-off. And the way that you do that is pretty straightforward. I'm just going to do lapply, which essentially applies the AIC function across each entry, each list entry in all models. So if I type in all models, hopefully my computer doesn't explode. Okay, so it's a list, and the list contains the regression result for the best for each of these models. So this one is rating, right? So the first entry in list is the regression on rating. The second list entry is rating and income, and so on and so forth. So basically, I'm going to look at the AIC of each of those models. I can also look at the BIC of each of those models, and I can look at the adjusted R-squared. This is kind of a weird way to do it, but okay. So here is our AIC, and just as a quick refresher, you want the smallest AIC possible. So what you'll see happening is that as you include more and more variables, the AIC is decreasing because the likelihood function is increasing, and it's subtracting the likelihood function, so it's getting smaller. But at a certain point, it starts going back up. So we can see So model 3 is decreasing, model 4 is decreasing, model 5 is still decreasing. At 6, it gets to 48.17, and then it starts going up because now it's starting to say, okay, the trade-off between the number of variables that you're putting in versus the likelihood measure in your model is now in the other direction. And so here I would say, okay, model 6 is my best one according to my AIC, and that model is, okay, wait, I think this will be easier. Okay, here. The model that is the age of the person, the number of cards they have, their credit limit, whether or not they're a student, and their income, and their credit rating. So if I include all of these variables, it's saying I'm getting the best sort of model, right? And so now I have this neat procedure where I have some combination of variables, and I am now able to apply this algorithm and determine which variables are best. Let's do that for the BIC instead of the AIC and see how that compares. So again, we're seeing a similar type of thing where you're getting a decrease. 58, 47, okay. And here what you see, and then it starts to go up at 6. So the BIC is actually telling you a slightly different answer, right? So the BIC says actually number 5 is the best model. So that would be here. So number of cards, credit limit, whether they're a student, their income, and their rating, but not including their age. So you can see that the choice of your criterion can have some kind of influence on what the ultimate model selection will be. So do keep that in mind. You can get different answers essentially by your selection of the criterion. And in fact, I'll sort of re-emphasize what I said earlier. The other criterion is to do cross-validation. And that can tell you as well how many variables that you should use. And again, I tend to think that's kind of the best way to do it. But we'll leave it at that. Okay, so the last one is to look at the adjusted R-squared. So here we can see marked improvements as I include more parameters. And then at a certain point, you'll notice it starts to decrease. Again, for the same reason, you've got your penalty function against number of parameters. And here, I believe this is our highest, although sometimes this can be nonlinear. That's 9961, still higher. Yeah, so number 6. So this one is in agreement with the AIC. In this case, it won't always be the case. But generally, there's also this idea that like there's like a threshold value between these guys, and that's not a hard and fast rule of thumb for anything, but you'll see like at a certain point, the marginal gains, it's definitely still improving the model without getting to decrease from the penalty, but they're pretty close, right? The adjusted R-squared as opposed to sort of down here. And the same can be said for the AIC, BIC. The values start to get pretty close. And so I think generally if you're within that range, you're gonna be getting pretty similar model fits, pretty similar predictive ability. But you know, we're picking the best one because it tells us the best one. Okay, there's a question here. Would you use stepwise selection and CV together, or are they exclusive of each other? No, you could use them. You could definitely use them together. And in fact, the stepwise is more of the strategy of like, I would characterize it as the cross-validation is a basically an additional criterion method, right? So it's like the AIC BIC adjusted R-squared. It is essentially the mean squared error out of sample. That's that's what the cross-validation is telling you. So these are all criteria to select the best model among a set of models. And then the stepwise algorithm is how to create a subset of models such that I don't have to test the criteria for every possible combination of models. So, so yes, you can use cross-validation in conjunction with stepwise regression. It's really kind of just an alternative criterion. So you can think of it as like another AIC, BIC adjusted R squared metric.
Hey,
Yeah.
Alan, quick question.
Yep.
I don't know if so I'm just wondering, like, hypothetically, in this case, if you had in your credit data frame, if you're missing like, say you're missing like rating for one given data point,
Mhm.
or like one given idea, I guess.
Yep.
Do you have to throw that out, or like when you're doing this stepwise analysis?
You don't explicitly need to throw it out. Actually, when you run linear model, and maybe I should have mentioned this when we're sort of on the linear model step in earlier lectures. If you have data missing, think about what that means for doing your regression. You have nothing to fit to because the data point is just not there. So actually, when you do LM over a set of data, and you're specifying like a column that has a missing point, it's going to just toss that out. So you don't need to do that explicitly. Yeah.
So given this, if we had a data point missing, this would all run the same.
Yep. Yeah.
Okay.
Exactly. Cool. Okay. So that was kind of a long roundabout way of doing it. I don't know. I generally think that understanding the algorithm and doing it yourself, which I'm forcing you to do on the homework, is the best way to really understand what's going on here. That being said, like if you do this in the future in your own research and stuff, you're not going to be writing out this crazy algorithm every time. There are built-in functions that do that. So I'm going to show that to you. So I'm going to create a new data set called credit hold, which is just credit, except that it throws out the ID column. That's all. Okay, so let's take a look. There's a shortcut in linear model. So if I wanted to run the model and include every single variable except the one of interest, instead of writing income plus limit plus rating plus cards plus age, so on and so forth, which can be kind of tedious, you can actually just include a period. And what that means is it says run it against everything else. So handy little shortcut. So I'll just show this really quick. Model, summary, model, and it's got everything in there. Okay. Step AIC is a built-in function of I'm pretty sure it's the mass package that I showed above here, which is why I loaded this library. And so what it does is it takes in a model. So this is this model here that I've already defined. And I am able to go actually in both directions. And by that, I mean, you can specify forward, or you can specify backwards, or you can specify both forward and backwards. And what it'll do is run through, and you'll see it ends up giving the final sort of same answer by getting to the lowest AIC. So this is my 6 variables that I estimated from here. So this is doing essentially the same thing as all of this. Yeah, but it's also kind of a black box, so I wanted to do this so at least you have notes about what the algorithm is doing, and you'd be able to review that. So that's step AIC. You can do the same thing for BIC, like this. So it's actually still called step AIC, but we're changing our penalty function for K. So here in the autocomplete, in this yellow thing, you can see there is a default of K equals 2, right? And so if you remember, AIC is equal to 2K minus 2 ln of my likelihood. So the K weight is here, and the default is set at 2. But I can change that as one of the options in this function. So it'll be the same thing, model direction equals both, and I want the log of the sample size, which is what we had defined, right, as BIC is equal to log n times K minus 2 ln something like this. Was there a 2? Yeah, there's still a 2. Okay. And so this will then, or should give the same as this. Invalid formula. Uh-oh. What did I do? Oh, I didn't specify the input correctly. K equals. Okay, it actually gave 4 instead of 5. Yeah, it's pretty close. Oh, this must be, okay, I know what this is. This is the backward step, not the forward step. Yeah, if you do both of them, it may give a slightly different answer. So when you go forwards versus backwards, you're not always guaranteed to have the same answer as well. Yeah, so there's a question, does specifying a quote unquote direction equals both allow the code to do both backward and forward stepwise regression? Yeah, that's exactly right. So you can say forward for just forward, backwards for just backwards, and both it'll go both ways, and then look at the lowest AIC going in both directions. Yeah, okay, so I think that basically concludes today's lecture. Again, make sure that you review this material. I went pretty quickly through the code, and it is one of the important procedures to have a pretty good grasp on. In the meantime, yeah, homework 2 has been posted, so go ahead and take a look at that. It'll be due next Thursday. Okay, there's more questions coming up. Which package contains the function step AIC? I'm fairly certain that's coming from this package, mass. If not, it'll be coming from stats. I think it's mass, though. Great. Yeah, so we'll end, 10 minutes early today. I'll stick around for a couple minutes in case anyone has questions.